All right, everyone, welcome. My name is Andrew Howard, and you are all here for Evan Sinukoff's PhD defense. Let me first just lay out the ground rules. I'm going to give a little bit of an introduction. Evan will give his defense. After that, we'll open it up for questions to the audience here, the audience in Hilo. The committee members should hold their questions until after the public question period, and then of course we'll have a private comment and question period. Assuming that all goes well, which I have confidence it will, we'll have a celebration for those in Manoa in the Moon Room, and I'm estimating that'll be sometime around 12:30 or so, but we'll send out an email to let everybody know. Okay, so I want to, by tradition, start this off with a little bit of an introduction about Evan. So I got a phone call from a number I didn't recognize in about April of 2012. And Evan was cold calling me because he had heard that I might be coming to Hawaii, and he was thinking about going to Hawaii. And so he wondered if we could work together. And so it was through that I started working with this guy. We both started in the fall of 2012. And Evan is part of a distinguished class that year of several astronomers who've already graduated and gone on to great things. Evan is graduating today and going on to great things, and we have a few more that will follow shortly. I want to give you a little bit of a feel for what Evan is like. And I think in many ways, one of the defining characteristics of Evan is as the Canadian astronomer. And that came through quite strongly, I think, at least for me, at the first Halloween here at IFA. This is Evan and his brother, who I'm told, although this seems way too good to be true, that they independently decided to dress up as lumberjacks. Evan will have to confirm or deny that at some point. And the next year, not to be outdone, Evan dressed up as Captain Canada. Which is just a truly remarkable outfit, if you ask me. Evan, I think, could make a claim for being the best hockey player in Hawaii at one point. On Oahu, there's of course only one rink, so there's not a tremendous amount of competition, but there is Evan playing there. I solicited some stories from some of Evan's friends and colleagues, and I got a good number of them from the fellow denizens of Aolani Place. This is just a few blocks from IFA, Evan's housemates. And perhaps I think the best story that typifies the Canadian-Hawaiian experience was, at one point, they're all sitting down to dinner at this dinner table, and somebody notices there's a cockroach crawling up the wall. So Evan runs and gets his hockey stick and apologizes to the cockroach. "Sorry, cockroach, sorry," and then whacks it. That's the perfect combination of Canadian courtesy in a Hawaiian environment. So Evan had many other fantastic experiences here. This was the year Eric Pettigura stayed for a year, and Eric's wife, Alana. Evan I think this was a birthday. Alana had a cupcake truck and would bring home free samples every day, and Evan ate a prodigious number of these cupcakes. Evan and Alana decided to fake adopt 2 dogs. Eric decided that he never wanted to have a dog, so as a prank, Evan and Alana jointly adopted them for several hours. To Eric's horror, they eventually sprang the truth. Evan is an incredible consumer of breakfast cereal. I'm going to guess maybe 2 boxes a day or so. He would get shipments from the mainland. They'd be piled up everywhere. It's quite an incredible consumption.
Some of that's Matt Hosek.
I don't believe it. So Evan, of course, enjoyed Hawaii too. Here is Evan enjoying himself working on the beach. Here's Evan hiking. I think Evan scoured many of the hiking trails around Hawaii. But what I'm most proud of for Evan is the astronomy that he's done. I think as you'll see in his presentation today, we've really learned something fundamental and remarkable about the universe through Evan's work. So Evan, I'm really proud of you for that. Here's Evan on the summit of Mauna Kea in front of the Keck telescopes. Just before this, I grepped our log sheets where we keep track of all the nights observing. And Evan was part of a major Keck observing program. And Evan observed 97 nights at Keck Observatory, which is really an incredible number. So Evan, you've not only put in the hours, but you've also delivered incredible results. Here's one of the other telescopes Evan used. This is the APF telescope. in California. So Evan, as you ride off into the sunset, I just want to preemptively wish you congratulations and best luck. And if you want to come up here now, I will give you this way. Everyone, Evan Sinukoff.
There's some contrast that I need to, yeah. Okay, thank you. All right. So thank you, Andrew, for that lovely intro. As you can see, it's nice to be back at the IFA. I have a lot of fond memories of this place, and it's nice to see some familiar faces and some new faces here. So I'm here to present my dissertation on the masses and properties of extrasolar planets. So first and foremost, I'd like to acknowledge this list of collaborators here. Much of this work is based on hundreds of hours of observing, meetings, analysis, a lot of hard work by these people. So most of my talk will be focused on small planets. And when I say small, I mean planets between the size of Earth and Neptune, 1 to 4 Earth radii. And specifically, I'm going to focus on small planets orbiting close to their host stars at orbital periods less than about 50 days. So that's about a quarter of an AU. And when I entered grad school, these planets had been labeled many things: super Earths, sub-Neptunes, mini-Neptunes. But these names imply a distinct composition. And the compositions, though, of these planets is a major puzzle. And so I've devoted much of my thesis to understanding the bulk compositions of these small planets. So this plot shows planet size versus orbital period. This is just 9 years ago in the pre-Kepler era. We only knew of a few small planets. That's not because they're rare, but because they're hard to detect. But then Kepler came along and gave us the first census of small planets orbiting close to their host stars. And suddenly, we found a huge abundance of small planets. You can take these detections, apply completeness corrections to compute intrinsic occurrence rates. And the intrinsic planet radius distribution found by Eric Petagira et al. In 2013 looked like this. The distribution peaks between about 1 and 3 Earth radii. So the takeaway point here is that initially from Kepler, we learned that small planets are extremely common. Nearly half of all sun-like stars host a small planet at an orbital period of less than 100 days. So this observation, though, of a large population of small planets orbiting close to their host stars posed fundamental challenges for planet formation theory. So this is a cartoon version of planet formation, and we're going to imagine a couple different scenarios for the formation of these close-in planets. So perhaps the simplest explanation is that these planets formed in place, so-called in situ formation. And in that sense, these planets would be scaled-up Earths with rocky cores. And if they formed before the gas dissipates from the disk, then the solid cores might accrete some hydrogen, helium, or some gas in their envelopes and balloon to a few Earth radii or more. But the inner protoplanetary disk has less mass, and it's debated whether there's enough solid material there to assemble planets much larger than Earth. Another possibility is that these planets form as scaled-down Neptunes, forming rapidly from material beyond the ice line and then migrating inwards to where we observe them today. In this case, we'd expect them to possess the ices that are present beyond the ice line and therefore be water-rich. So you can see that the bulk compositions of these planets provide a direct link to their formation and evolutionary history. Most of what we know about the bulk compositions of these planets comes from measuring their masses and radii. So for example, on this plot of radius versus mass, I'm going to call this the mass-radius diagram. The curves show the mass-radius relations for planets of pure iron down here, pure rock up here, and an Earth-like composition in the middle corresponding to about 30% iron and 70% rock. And based on the mass and radius measurement of this particular hypothetical planet, we can infer that it has a near Earth-like composition. So we have thousands of planet radii measured by Kepler, but only a few dozen precisely measured planet masses. And this has to do with the techniques we use to measure the masses of these planets. So most planets to date come from measuring the radial velocities of planet-hosting stars as they orbit their common center of mass between the planet and the star. And this motion induces a Doppler shift in the stellar spectrum that we can measure. But only a handful of Kepler planet hosts are bright enough for precise radial velocity measurements. Masses can also be measured from transit timing variations, and this is caused by the mutual gravitational interaction between planets in the same system. But of course, this requires there to be, for it to be a multi-planet system, and the signals tend to typically be too weak to measure unless the planets are near orbital mean motion resonance. So as of 2014, the most complete catalog of of mass and radius measurements was constructed by Lauren Weiss and Jeff Marcy, most of them coming from a survey of Kepler planet host stars. So the left plot shows planet mass versus radius. On the right, planet density versus radius for 65 exoplanets smaller than 4 Earth radii. I'm going to focus on the right plot here, density versus radius. I find it more intuitive. So the gray points are masses measured by radial velocities. Orange are TTV masses. The larger circles are more precise measurements. And the green curve corresponds to an Earth-like composition. Just ignore the rest of the legend for now. So what does this plot tell us? Well, the largest of the rocky planets are between about 1.5 to 2 Earth radii. As you move to the left, the density drops as the rock gets less compressed, and planets like Kepler 78b and Kepler 10b obey this rocky trend. As you move towards the right of this transition, planets have more gas, and the density drops. And by the time you get to Neptune size, planets are mostly gas. So this study gave us a first-order representation of the mass-radius diagram, the first statistical evidence for a transition from rocky to gas-dominated planets. But there's considerable scatter, you can see, about the mean mass-radius relation, and some noticeable outliers. For example, like this one, Kepler 138d, particularly low-density outlier. And this diversity suggests that the planet mass-radius relation might be partially driven by environmental factors, perhaps temperature and properties of the host star maybe. So a major clue was discovered last year by members of a research team. They revealed the finer details of the planet radius distribution by precisely characterizing the planet host stars. So planet radii are measured in proportion to stellar radii, and the stellar radius uncertainties in the Kepler catalog were large, typically about 25%. And so this dominated the uncertainty on the planet radius. You can see the typical error bar here. So if there are any sort of finer details in the planet radius distribution, it would be blurred out by our measurement error. But then the California Kepler survey, including many of my collaborators, collected Keck-Hira spectra of more than 1,300 Kepler planet hosts and shrunk the typical uncertainties on stellar radii down to about 10%. And this revealed that there are actually 2 distinct populations of small planets. The planet radius distribution is bimodal, with peaks at roughly 1.3 and 2.6 Earth radii, and a valley in between. This has been dubbed the planet radius valley, which separates super-Earths from sub-Neptunes. So before these terms had been used sort of interchangeably, but now we have a more precise definition that's observationally motivated. So why does this valley exist? Well, we think that the main driver is photoevaporation. So this graphic demonstrates the effect. Hope the contrast is okay here. So during planet formation, planet cores assemble from solid material in the disk, And as they grow, they accrete a gaseous envelope. But the X-ray and ultraviolet radiation they receive from their host stars can erode this envelope, mostly in the first 100 million years of the star's lifetime. Now, models show that the timescale of this photoevaporation is longest when the radius of the planet envelope is about twice that of the planet's core. So envelopes that are initially more extended than this tend to erode until the radius is twice that of the core, forming a population of sub-Neptunes with envelopes that are a few percent hydrogen and helium by mass typically. Planets that form with more tenuous envelopes, corresponding to the bottom rows here, are completely stripped of all their gas, forming super-Earths with a gap in between. And the fact that the peak occurs at about 1.3 Earth radii tells us something. It tells us that the typical core radius is about 1.3 Earth radii. Now, the mass of a core depends on its composition. So Owen and Wu, 2017, showed that the mass of a core composed of water ice, for example, is too low to retain enough gas for planets to occupy the second peak, at least in equal height. So as you can see here, we'd need about a 2 Earth radius ice water core in order to maintain a second population at equal height. An iron core, on the other hand, would be too massive, and there wouldn't be enough photoevaporation unless the typical core size was smaller than an Earth radius, which it's not. So according to photoevaporation models, in order to best match the observed radius distribution, cores need to have roughly Earth-like compositions. So this is an indirect method of inferring composition that relies on photoevaporation models, but it does suggest, for example, that water-rich planets are rare, and that most planets form with Earth-like cores surrounded by hydrogen-helium atmospheres, which are then sculpted by photoevaporation. It's important to note that it's also unlikely that these envelopes would be made of heavier elements, like water, for example, because these would be typically too heavy and too resistant to photoevaporation. So before we move on, here is a portrait of small planets. They're common close to stars. They often come in multi-planet systems. They're mostly on low eccentricity orbits. There are exceptions. They might have formed in situ, which would favor hydrogen-helium-rich envelope, or via migration, which favors a water-rich composition. There's a transition that's been observed from rocky to gaseous planets between 1.5 to 2 Earth radii. The planet radius distribution is bimodal, which has been interpreted as the photoevaporation of tenuous hydrogen-helium atmospheres surrounding Earth-like cores. And this suggests formation interior to the ice line. And some key questions remain. How does this transition between rock and gas-dominated planets depend on environmental parameters like temperature, stellar properties, for example? Can we see the effects of photoevaporation in the mass radius diagram? We certainly expect that we should. And what is the diversity of planet core masses and compositions? Does it depend on the metallicity of the host star? We really need more measurements of the masses of small planets to address these questions. And that brings me to the K2 mission. So as most of you know, in 2013, the Kepler telescope lost a second reaction wheel, leaving it with just 2 working ones and unable to point stably. But engineers devised a way to balance the telescope, but it required that the telescope be pointed at a different patch of sky every 80 days along the ecliptic. So the K2 mission was born, and so far it's collected precise photometry from 18 different fields or campaigns. I'm part of a large K2 collaboration, which has detected and validated hundreds of planet candidates. We do everything from proposed K2 targets to planet searches and validation of planet candidates. And this framework really provides the support we need to ultimately produce a well-vetted planet catalog. And for a subset of these planets, we can conduct follow-up radial velocity observations to measure planet masses and densities. A collaborator, Eric Pettigura, developed a specialized pipeline, photometric pipeline, to generate clean K2 photometry and search for transiting planets. A couple of them are shown here. We derive our stellar parameters, like effective temperature, metallicity, masses, radii, from Keck high-res spectra, which we collect for each star. Before candidates can graduate to this planet catalog, though, they need to pass a series of validation tests. So we're basically looking for stars that are blended within the aperture that can cause either the false detection or mischaracterization of a transiting planet. We, for example, search the stellar spectra for multiple sets of stellar lines. We also obtain AO images of planet candidate hosts, all of them, to identify nearby companions. So our team has published several planet catalogs, K2 planet catalogs. I've listed a couple here. I was lead author on a catalog of 11 multi-planet systems from the first 2 K2 campaigns. This plot shows our planet catalog in radius versus orbital period, and we identified about 60 of these as suitable planets for RV follow-up. Of course, we're going to need a lot of observing time to take our RV measurements. So in a proposal led by Andrew Howard, NASA awarded us 40 nights on Keck high-res over 4 semesters to measure the masses of small planets from the K2 mission. And this constituted an official NASA Keck key project. So we also have supplementary time from our local institutions, Caltech, Hawaii, and UC. And the goal of this project was to measure the masses of roughly 40 small planets from K2. And this would roughly double the number of small planets with well-measured masses. So we collected, over the course of 3 years, more than 1,000 radial velocity measurements. Here's an example of one of the many RV time series we collected. In this case, the star is K2-106. It's a G5 dwarf that hosts 2 transiting planets. Planet B orbits every 13.7 hours. It's an ultra-short period planet with a radius of 1.8 Earth radii. And we have roughly an 8 sigma detection you can see in our phase-folded RV time series. There's a second transiting planet at 13 days, 2.8 Earth radii, and we have a 2 sigma detection of this planet, and it appears to be lower density. So I can't show you all of them, but in total we measured the masses of about 50 new planets. So Andrew is preparing, and Andrew and I are preparing a catalog with these new masses. And as the last chapter of my thesis, I've analyzed the updated population of small planets with measured masses, which is now much larger. And with this larger sample, I can address some of those key questions about the compositions of small planets. So my goal was to assemble a catalog of all planets between 1 and 8 Earth radii with measured masses, including those from the literature, then precisely and uniformly characterize their host stars, and then re-examine the mass-radius relation and its dependence on things like temperature and host star properties. So this shows the overall flow in constructing this planet catalog. Again, I merged measurements from the literature with our key project sample. The numbers indicate the number of planets coming from each of these 3 sources. On the literature side, I first queried the NASA Exoplanet Archive, or NEA. But the NEA is not totally up to date. Most noticeably, it's missing a catalog of 145 Kepler planets with TTV masses measured by Haddon and Lithwick, 2017. And for that, I kept all planets for which the mass measurement was independent of their choice of prior, eccentricity prior specifically. And then another 50 or so planets come from our K2 key project sample. We obtained a high-res spectrum of every single one of the planet host stars and used them to determine effective temperature, metallicity. We incorporated Gaia parallaxes to measure precise stellar radii with typical errors of about 5%. I computed planet masses, radii, and also planet core masses. To measure planet core masses, we adopted the planet structure and thermal evolution models of Lopez and Fortney, 2014. So they simulated the radius evolution of a population of planets with Earth composition cores surrounded by hydrogen-helium envelopes. And they did this over a grid of planet masses, core mass fractions, and incident fluxes. So we used our measured masses, our measured radii, incident fluxes, and ages, and interpolated this grid to estimate the core mass fractions of our planets. And it's important to note that for small planets, the core mass usually is most of the total mass. In the end, the final catalog consists of 139 planets orbiting 101 different stars. The stars span a wide range of effective temperatures, from early M dwarfs to late F. The majority of the stars are main sequence, although we do have a few subgiants. Almost half of these stars have a single known transiting planet, while the other half are multi-planet systems. Here I'm showing planet radius versus orbital period. Note the logarithmic scale and period here. Blue corresponds to planets with RV masses, orange are TTV masses. And we distinguish planets by their radii. So we have sub-Saturns, 4 to 8 Earth radii, sub-Neptunes, 2 to 4 Earth radii, and super-Earths, 1 to 2 Earth radii. And we note here that sub-Saturns are actually overrepresented in our sample. In reality, planet occurrence drops once you get above sub-Neptune size. But we have more sub-Saturns here because there have been specific programs to target sub-Saturns and measure their masses. And now for some key results. So we have an updated mass radius diagram spanning 1 to 8 Earth radii. Again, note the logarithmic scale and mass. The size of the point scales with the measurement precision. And in addition to curves for pure iron and Earth-like composition, I also included curves corresponding to Earth-like cores that are surrounded by different amounts of hydrogen-helium envelope, from 1% all the way to 40%. So for super-Earths, you can see a range of masses between about 1 and 10 Earth masses. The majority of them seem to straddle this Earth-like composition curve, but more on that later. The sub-Neptunes have masses from a few to about 15 Earth masses, and they tend to have envelopes of a few percent hydrogen helium. And the sub-Saturns are more widely dispersed, from a few Earth masses all the way to about 60 Earth masses. They're generally 10 to 50% hydrogen helium by mass. But I really want to focus on the small planets. And so I'm going to zoom in and show you a really exciting result. So here I'm plotting planet density versus radius. Points are colored according to incident flux. The background shading scales with the number density of points, weighted by the measurement uncertainties. I also applied a Gaussian smoothing filter. And at first glance, the density radius distribution sort of appears bimodal, and there appears to be a gap in planet composition. We can clean this up a bit by removing planets with large mass measurement uncertainties, and the gap becomes more apparent. On one side of the gap, there's a cluster of super-Earths, consistent with rocky cores and little to no atmosphere. Most of these receive more than about 100 times the irradiation that Earth receives, so they're particularly susceptible to photoevaporation. And on the other side, we have sub-Neptunes, a population that's consistent with rocky cores surrounded by hydrogen-helium envelopes, a few percent by mass. And the gap appears where you expect to find the more tenuous envelopes that are less than about 1% hydrogen-helium. And this suggests that such atmospheres are completely stripped by photoevaporation. Interestingly, there is a small population of 1 to 2 Earth radius planets with lower densities that are consistent with less than 1% hydrogen-helium atmospheres. But these planets are relatively cool and less susceptible to photoevaporation. So this is the first time that a gap in planet compositions has been directly observed in mass radius space. It strongly supports the claim that the gap in the planet radius distribution is the result of the complete photoevaporation of small planets with small hydrogen-helium envelopes. Another key result is the distribution of planet masses and core masses in our sample. While the observed core mass distribution peaks between about 6 to 9 Earth masses, smaller cores are likely somewhat underrepresented in our sample due to their lower detectability. So this might shift or raise the points at lower masses up a little bit. On the other hand, the steady drop beyond about 10 Earth masses is real. The majority of cores exceeding 10 Earth masses actually belong to subsaturns, which, on the other hand, those super-Earths and sub-Neptunes, which comprise the bulk of the planet population, rarely possess cores larger than 10 Earth masses. This is an important constraint for planet formation models. Here's a plot of core mass versus orbital period. At orbital periods less than about 3 days, cores do not typically exceed 10 Earth masses. We have no instances of that here. From 3 to 10 days, most cores are still less than 10 Earth masses, but there is a large diversity ranging from about 1 to 50 Earth masses, and this is mostly due to the diverse subsaturn population. Almost all of the cores in the TTV population are less than 10 Earth masses, and this could be because these larger cores appear are the result of collisions and mergers caused by that result from the dynamical excitation of planets onto eccentric orbits, which then naturally would not tend to form resonant chains of planets for which we can measure TTVs. And if we just look at the ultra-short period planets with orbital periods less than a day and plot them on the mass radius diagram, we see that they straddle the boundaries between Earth-like and pure rocky compositions. Ultra-short period planets provide a clean sample of stripped rocky planet cores, and it's unlikely that they would have hydrogen and helium atmospheres. These would be unlikely to survive on such highly irradiated planets. So these are a good sign that cores typically don't grow much larger than, at least of small planets, don't grow much larger than 2 Earth radii and more massive than about 10 Earth masses. Another goal of this thesis was to constrain the diversity of core compositions. So we analyzed the sample of super-Earths, which are likely to be bare cores, highlighted here. And we first assumed that the cores are comprised just of a mixture of iron and rock. And we asked the question, given our measurement uncertainties, could these planets all just have a single composition with some particular rock mass fraction, which I'm calling F rock? To conduct this test, we basically, I won't go through all the details, we basically simulated a population of planets that have the same masses as our measured masses, but the radii we compute assuming a specific rock mass fraction, in this case 0.7, which corresponds to an Earth-like composition. To simulate observations of these planets, we draw 1,000 mass and radius measurements of each simulated planet, assuming the same noise properties as our real mass and radius measurements. So for each draw, we compute F rock, and then the same steps are repeated using the observed masses and radii and their uncertainties. And we can compare the results. So the gray histogram shows the real observed F rock distribution, and the green corresponds to the simulated population where we assumed an Earth-like composition. And you'll notice we allow F rock to be greater than 1. We do this using an analytic continuation, and this basically allows us to handle the low-density planets that are less dense than pure rock. So a couple things to note. First, the median of our observed F rock distribution is 0.82, so 82% rock, 18% iron. The observed distribution is broader than the simulated one. And this suggests that there is an intrinsic spread of core compositions that our measurement uncertainties can't account for. And some of these are Earth-like. And this, if you think about it, is consistent with the terrestrial planets in our solar system. In the second scenario, we assume that the cores are composed of water ice and rock. And we ask the question, what fraction of cores are more than 10% water by mass? So to estimate this, we again randomly sample the mass and radius posteriors of each planet 1,000 times. We compute the water fraction, using the equations of Fortney et al. And for each planet, we then compute the fraction of these draws where F water was greater than 10%. And we take the average of all these values. We find that at most, 18% of these cores are comprised of more than 10% water. And this suggests that most of them form interior to the ice line. Finally, another exciting result is that planet core mass is positively correlated with stellar metallicity. Here I'm showing core mass versus host star metallicity for the entire sample of 1 to 8 Earth radius planets. And we find a correlation coefficient of 0.39 with a p-value of 2 times 10 to the minus 6, suggesting this correlation is indeed significant. Metal-poor stars, less than about 0.2 dex, rarely seem to produce cores exceeding about 8 Earth masses. And perhaps there's not enough solid material in the disk of these low metallicity stars. It's also important to note that we can't just assume a continuum of planet formation right from 1 to 8 Earth radii, as you might suggest from this steady trend here. Planets, most notably the sub-Saturns, for example, are intrinsically much rarer, and they might have entirely different formation pathways, which with high metallicity thresholds, for example. So, just looking at planets smaller than 4 Earth radii, the super Earths and sub-Neptunes that dominate the planet population, we see that this trend remains significant. So this is really a sign that the assembly of cores, including those of small planets, is fundamentally limited by the solid surface density in the protoplanetary disk, which scales with the metallicity of the host star. But it's important to consider that stellar metallicity is strongly correlated with stellar mass. And this is because high mass stars have shorter lifespans, so those that we observe today tend to form relatively recently when the galaxy was more enriched with metals. And it's plausible that core mass would depend on stellar mass. It's believed that the more massive stars have more massive disks, and thus a larger reservoir of solid material to form planets. So which is a better predictor of core mass? Is it stellar metallicity or is it stellar mass? We find that core mass is better predicted by stellar metallicity than stellar mass. So on the left you see a plot of core mass versus metallicity, the same one I showed before, and here's the same one on the right, core mass versus stellar mass. And you see that the correlation is much tighter for core mass versus metallicity than it is for stellar mass. We also checked just the population of super Earths and sub-Neptunes, and again, you can see the correlation is tighter for core mass versus metallicity than it is for core mass versus stellar mass. So, to recap, we've doubled the number of small planets with measured masses and updated the mass radius diagram. We've found a gap in planet compositions, a deficit of planets with tenuous atmospheres, suggesting that atmospheres are completely eroded, or that these tenuous atmospheres are completely eroded by photoevaporation. And we've discovered a correlation between planet core mass and the metallicity of the host star. And with that, I just want to wrap up and acknowledge a few people. First and foremost, Andrew. It's just been a dream come true to be a planet hunter and working with you and your team. You're one of the best leaders I've ever known, and it's just been a real thrill to work with you, and I appreciate all your support. Thank you to my committee, Christoph, Jessica, Mike, and Jeff. A shout out to my research teams. I hope some of them are listening from the California Planet Search and K2 collaboration. Jessica was also my 699 advisor. It was great hunting for stellar mass black holes. And then there's some people who I consider have been mentors to me throughout the years. Eric, DJ, Howard, and Ian. I'd also really like to thank some of the IFA staff. Bill, Faye, Laura, Diane, Kristen are all people I've worked closely with. Thank you for all that you do. The IFA grad students, my cohort, postdocs and faculty here, and to my friends and my family, especially my parents. My mom and dad are here. I really appreciate their love and support. And my girlfriend, Jacqueline. This is the end of the long distance part of our relationship, and I'm really excited to move back to Toronto with you. So thank you very much. I'll take questions.
Why don't we start out in Hilo with questions? Do you there want to kick things off? All right. Well, while you guys are thinking of it, we'll take some here. So, anybody in the audience?
So this is sort of a technique question, something dear to my heart. Until this year, you didn't have distances to most of the Kepler stars. How much does the inclusion of distance information improve the radius measurement of the star?
Significantly. I mean, we have the Gaia parallaxes, so all you need to do is take our use the Stefan-Boltzmann equation basically, and we have very precisely measured effective temperatures to order 50 Kelvin. When we combine those with our distances, all we really need then is an apparent magnitude in K-band we use, and to give you a sense of how much it improves things. When we run everything without the Gaia parallaxes, the typical uncertainties were about 10%, and this brings them down to about 5%.
More questions? Gene?
How sensitive is your core mass metallicity correlation to any observational biases you've got just from your sample selection?
So one thing we were particularly concerned about, I'm actually glad you asked this. I think I have a backup slide for this. Yes. So there's been, for example, one thing we were worried about was maybe we're just less susceptible to smaller planets orbiting higher metallicity stars, which tend to have the lower mass cores, and so that sort of forms a gap here. So I guess back to this point, that might explain this gap down here. There's no detection biases that would explain the gap up here, but so what we did was we checked to see if there was a correlation between the planet radii and host star metallicity, and we found that I think we toggle back and forth. We have some smaller planets around high metallicity stars, and it's really just when you shift to mass space that this trend emerges. Just toggle back and forth. We think it's unlikely that it's due to a lack of small planets around high metallicity stars that we're detecting.
Great. Amy?
So I thought it was really interesting how you were saying that you're assuming that most of the planets, all these small planets, have, even some Neptune ones, have Earth-like cores. And I was wondering how much, or what is known about Neptune's core and that transition from sub-Neptune to Neptune?
I guess I might be the wrong person to ask about Neptune's core, but I assume it's water-rich. It formed beyond the ice line. Here we're observing a population of planets that are close in, and what sort of the planet radius distribution and what the plots I've shown you are showing is that you don't need water to explain these planets in their core or their atmosphere. There might be a fraction of them that are water-rich, but at least the bulk seem to not be water-rich, and that could be because this population that ends up close in, where we are sensitive to, formed interior to the ice line, unlike the ice giants in our solar system.
So Neptune would really be that transition point. So we're just wondering, can you say anything about when you would have a Neptune-type system relative to the distance out?
I think it just all depends on formation relative to the ice line, which I think those are still the fractions of planets that form as a function of orbital distance and the various migration mechanisms that can bring them inwards. That's still not super well constrained, and so I hesitate to make any firm comments.
Sam?
Yeah, sort of related to that. I was just wondering, So you showed that if you allow for this, this F rock, right, you find that most stars, or most cores, sorry, don't need water in them to be created. But did you try like modeling something with F water and F iron instead of F rock? So if you change the potential composition of the core, there are some degeneracies, depending on which materials you choose. Is there anything that you could say to be like, oh, these have to have rock versus, they could be some mix of water and iron?
That's right. That's a valid point. There are degeneracies in core composition, even for an exact mass and radius measurements. The main reason we used rock and water and iron and rock is those were the best models available. I'm trying to imagine if we did have iron plus water, I guess that would open the door to slightly more water in the atmosphere. I'd have to go through that.
I'm not exactly sure where on this, relative to the snow line that would actually exist. But
yeah, it is possible that we can do a more complete, have a more complete suite of planet archetypes and admixtures that we're testing.
Yeah.
This diagram to the eye doesn't look like much better than a scatter diagram.
I can assure you we have our p-values and our
Yeah,
correlation coefficients, and they are uncertainty weighted. So part of what could be throwing you off is it's hard to really capture the error bars when just looking at it like this. So maybe another plot where it's like point size or something scaled with the error might be more visually impactful, but statistically it's robust.
Your correlation coefficient was what?
For the full one, it was 0.39. I don't have the just off the top of my head. It was something similar, and there's a smaller number, so it's less significance, but still very significant.
So the Hubert-Reeves the Hubert-Reeves test, another Canadian, is that if you let your worst enemy take away 10% of the points, does it still correlate?
Yeah, that would be another good test. I expect that as missions like TESS come along, they will populate this with many more planets. We're sort of somewhat limited in our sample size. This is but we're doing the best we can with the data we have, and this is something that in the future can be more rigorously tested. But with all the data we have, it certainly suggests the correlation is there.
Another question?
Did you find the relationship between core composition and whether they belong to a multi-planet or single planet system?
I have not done that test yet. That's something I could try. If single planet systems tend to be more excited sort of dynamical histories, for example, compared to multi-planet systems, which would maybe require more of a quiet formation, then there might be some compositional differences that you might expect. But I have not. There's like an infinite number of parameters I could try to find relationships with, and I've stuck to a few for now.
Hilo, any questions? Anything else here from Manoa? All right, well, let's thank Evan one more time. And a reminder for those here in Manoa, we'll send out an email